Hi, my name is Mio Shash, and today I'll be presenting to you Physics 2212's Lab 3 bar magnets. An introduction and preview of our lab. The purpose was to measure the magnetic field strength changes with distance from a bar magnet. We compared experimental data with theoretical predictions for both on-axis and off-axis magnetic fields using the Biot-Savart law. We calculate the magnet's dipole moment based on the data collected. A preview of our main results was that the magnetic field measurements followed an inverse cube law consistent with dipole behavior. A slope of negative 4.5 was obtained from a logarithmic plot of magnetic field strength versus distance, and the magnetic dipole moment was calculated to be approximately 1.99 amperes meters squared. Moving on to the models and assumptions. Our experimental model setup involved one magnet, a meter stick, and the Phi-Fox mobile application. The computational model was coded in WebV Python, and our assumptions was that the bar magnet will act as a permanent magnetic dipole. Here's an overview of the fundamental physics principles that we used for this lab. The Biot-Savart law is illustrated right here. It is used to calculate the magnetic field at a point in space due to a current element. The magnetic field is proportional to the current L and the length of the current segment dl. The direction of the magnetic field follows the right-hand rule as well. Here's an overview of each variable. The experimental setup and procedure. For the setup, we aligned the phone so that the magnetometer's x component reads 0. We had the on-axis magnetic field measurement by measuring the distance x between the magnet and the magnetometer at the magnetic field strengths of 20, 70, 120, 170, and 220 torrs, repeating this for 3 trials. The off-axis field measurement was as follows. We applied this measured y distance to the magnetometer at a 45-degree angle from the bar magnet. We measured the magnetic field at this location and we repeated this process for 3 trials. The system was the observation point, as is the magnetometer, and the surroundings where the experiment involves the bar magnet and the Earth's magnetic field. Any other forces or external magnetic fields are ignored, and the bar magnet was treated as a magnetic dipole. And here's a little diagram. Here's our data and results. As we went through the lab, we filled in each of these cells as we went through our trials, and little by little it illustrated this graph, and we can see our slope right here of negative 4.5 and some other calculated data from the spreadsheet that was provided to us. A walkthrough of the code. We have our constants here. This function created the magnet at the origin. This function calculated the magnetic field. This allowed us to visualize the magnetic field on axis and perpendicular to the axis. We modified the colors here. Moving on throughout here, it was the same functions, and then we visualized the magnetic field 45 degrees off axis, and then printed some statements in the visual output. Here's the visual output and the discussion. The conclusions. As the distance from the magnet increased, the magnetic field decreases, and vice versa. The sources of error were human error in placing the phone in inconsistent positions, slight movements or inaccuracies during data recording, and then measurement inaccuracies when determining distances. Finally, an interference from other magnetic sources, in my opinion, was one of the largest sources of error. Discussion. What if we hadn't oriented our experiment to compensate for magnetic north and instead laid out our meter stick at some intermediate angle with respect to Earth's magnetic field? If this had happened, I believe that Earth's magnetic field would significantly interfere with the bar magnet's magnetic field, which would likely distort and affect the accuracy of our final results. Next, what if we were to stick 2 identical magnets together, end to end, and run the experiment again? If this happened, I believe the magnitude of the resulting magnetic field would actually double, but the direction of the field would not change. Thank you.